Hello, my name is Peter,
And I'm Sean.
and we're doing Vesc data logging. So, what is Vesc? So, Vesc is an open source electronic speed controller, mainly used to control brushless electric motors on personal electric vehicles, or PEVs. In order to drive a motor, the ESC, or electric speed controller, converts battery voltage into alternating current that brushless motors like to accept. And what's special about Vesc is that it has the ability to read and change parameters about the vehicle status. So why is Vesc data important? Well, it's good to know what is going on at all times. The rider should be protected and should know the Vec's limits, especially under high load. I once had a fall that I landed on the back of my head. The helmet pictured in this was from that crash, and I had to go to the hospital for that. The left two pictures describe a catastrophic failure from a Vesc with an internal short, and there were flames that came out of the bike, and it was unfortunately recorded. The middle Vesc shows user error where I draw sustained peak rated current. It would have been useful to see temperatures approaching failure point during riding. The right PCB shows a blown DRV chip, which drives the MOSFETs for the motor. The message from Discord shows a friend who got stranded because a large bump destroyed their Vec's microcontrol unit. Some related work to our project is the Robogachi data recorder, which is a hardware device that connects to the Vec's UART line and stores the Vesc data directly into SD cards. So if there's a catastrophic failure, like a fire, it acts like a black box from an aircraft. So all that data will be stored separately from the catastrophic incident. The official Vesc tool shows the immediate values in a practical, space-inefficient way, which often is hard to see relevant data when writing. There exist iOS closed-source apps that address the shortfalls of the official Vesc tool, which unfortunately are closed-sourced, and we decided to redo what they're doing. But it serves inspiration. So an overview of our pipeline is that we have three components of our project. So first is the Vesc itself, which has a UART port that allows it to connect to peripherals like a Bluetooth module, which in our case is an intermediate device that takes the UART signals and converts it to a Bluetooth low energy signal. And then the third component is our Android app and phone, which will connect to the Bluetooth module, and through Bluetooth Low Energy, is able to communicate to the Vesc over UART and request the telemetry data and parse it on the Android app.
In terms of features, the app first scans for any nearby Bluetooth Low Energy devices, and then the user can select the Vesc to connect to. After the user selects the Vesc, the app will then request and graph data from the Vesc in real time, and the user can change which parameter they're viewing the graph for, and they can also change the time window that the graph uses to show a specific amount of past data. Some parameters, min, max, and average data points, can be seen on the third tab, the rightmost tab, as well as the most recent data points for 4 parameters can be seen on this data tab. The logs can also be exported from the Files tab, which creates CSVs of all the data collected by the app since startup. Next, we're going to show a live demo of the app side by side with a video of Peter riding a skateboard. So the app starts on the Connect tab, and the user has to press the scan button. Then all the nearby Bluetooth low energy devices show up, and the user can select the Vesc. Once the Vesc is selected, then the data will begin to show up on the graph. So here we can see that the battery voltage is around 47.4 volts, and it's changing by a little bit as new data points are being graphed. Also at the bottom, there are a couple different data points that are being displayed live. So these are the most recent data points for voltage, battery current, RPM, and MOSFET temperature. Of course, RPM and battery current are 0 because the skateboard hasn't started moving. At the top, you can see that we just changed the time window for the graph from 5 seconds to 30 seconds. And then again to 60 seconds. Now on this third tab, there's the export button, which we'll show later in the demo. And there are also 3 sets of min, max, and average data points for battery current, RPM, and MOSFET temperature. Now we show switching the parameter to battery current. So it's still 0 because the skateboard hasn't started moving, but you'll see that in this live demo, as Peter starts moving, the battery current increases, and then it'll decrease slightly as he slows down. And we'll show RPM as he comes back. And then when we change the time window to be 60 seconds, you can see basically the entirety of Peter's trip down the hall and back. So his RPM increases and then also decreases and then gets negative to about negative 5,000 before coming back to 0 when he stops. So now we're going to export this data using this export button. And when the user clicks export, then the file will be created using a timestamp, and it'll show up in the phone's document folder. And this is what the CSV will look like. Yep, and there are all the values that were recorded from the Vesc since the app connected to it. In terms of challenges, the first challenge that we ran into was just getting started with developing with Android. This was the first time that either of us had ever developed with Android. So we were familiar with Java, but it was particularly difficult understanding how the UI elements connected to code, and also actually learning how to code the UI elements, particularly when you have things like callback functions for buttons, for example, and when they need to work with information that might not be available at compile time. Just learning how to handle all of the data. Another challenge was getting the Bluetooth Low Energy on the phone to actually connect and request packets from the Vesc motor controller. In particular, we had a bit of difficulty getting the checksum correct. Eventually, we started by adapting existing code from the official Vesc tool, but there was a small misunderstanding we had that prevented any messages from being sent in response to our request. So when you don't have a correct checksum, then what happens is the Vesc just won't respond at all. So there's no real indication that you're even close, and that was a pretty difficult part in getting this whole thing to work. Also after that, we had to understand the Vesc UART protocol, which wasn't that difficult. It's pretty much we need to understand which they're called characteristics in the Bluetooth Low Energy corresponded to the TX and the RX lines for the Vesc UART. And then also we could look up online through the Vesc documentation or through their code how to actually parse the packets that we were receiving. Additionally, one thing that was a little difficult was getting GraphView to display the data smoothly, but we were able to figure that out by the end. And you want to talk about the mechanical failure you had?
So the mini bike, unfortunately, is no longer right now. So the work we have done this semester is great, but for future work, some additional features such as adding GPS location data and more ways of visualizing data like data gauges or larger text or adjustable text or maybe changing contrast or color that will aid a writer in shaky conditions to actually see the data would be very helpful. And then we could also add some phone sensors such as accelerometer, gyroscope, and barometer to the data recording to have additional sensor data in our recording.